Hello and welcome. Today we're going to code the Mandelbrot Fractal. But before we actually start coding, I will go over the maths behind that wonderful fractal. So just bear with me for a few minutes. It will be a lot easier to implement the code once you actually understand what's going on. So how do we get that beautiful fractal? Well, we get it from the Mandelbrot set. And a Mandelbrot set is given by this function. It is a set of complex numbers. So C is our complex number and Z is our real number. And that set of numbers should not diverge to infinity, that is, the values should not shoot off into infinity. And we start from 0, and then on the next iteration we calculate the new value using that same function. So let's actually see what happens further. So this is our function, f of z equals z squared plus c. And c is our complex number, z is our real number, and we start counting and we start doing our calculations from 0. That is the 0th term. So let's check what happens. So we have f of z 0th, and that's just c, right? 0 squared is 0 plus c. And this is our z first term. So then what we do is we plug that value in to the function again. And we get c squared plus c. Now let's take a closer look at what c actually is. So it is a complex number of the following form. So it is a plus b I, where a and b is any real number and I is our imaginary number. So I equals square root of -1. So in other words, a complex number consists of a real part and of an imaginary part. So real part of c is a, and an imaginary part of c, well, that's just b. And these two numbers is what we need to calculate when we want to get the Mandelbrot set. But actually, let's take a closer look at what happens here. So we have c squared plus c. So what is c squared? Well, that is a, as we have seen here, plus bi squared. Well, that equals to a squared plus 2abi plus b squared times I squared. And that equals to a squared plus 2abi. And you see here we have I squared, and what is I? I is the square root of -1. And square root of -1 squared is minus 1, so we get minus b squared. And if we continue, and let's rewrite the equation, so we have a squared minus b squared plus 2ab I. And now take a closer look at the result. So what is this? Just think for a few seconds. It looks very familiar, right? Why? Well, it's our complex number. It has a real and it has an imaginary part, so a minus b squared is our real part and 2ab is our imaginary part. So it is a complex number. And that is what we need to calculate in order to find the Mandelbrot set and then draw the Mandelbrot fractal. And as we know, we have an x and y axis. So we have our coordinate plane, and usually that's our y. But when we're dealing with complex numbers, this actually becomes our I axis, our imaginary axis. So instead of having real numbers along the y-axis, we have imaginary numbers. So I, 2i, etc. And our x-axis stays the same. So it's an axis with real numbers. And when we're dealing with a Mandelbrot set, what we actually want to do is we want to calculate the values between -2 and 2. So our Zn should be less than -2 and 2. So we have -2 here, and what we should do is just calculate the value somewhere here. So let's actually get into coding and implement all of this. So I have already created the project. I have used the Raylib project template. The only thing it does right now is just creates an empty window. So let's start adding new code. So as we have discussed earlier, we need to add the Mandelbrot range. It is a range between which we're going to calculate the numbers for the Mandelbrot set. So I'll just create a few more constants. That will be max, min, we're going to start from -2, and max, we will end at 2. Then we actually need to know how deep we should go, so depth, and that will be the number of iterations, and we will just set it to 100. So the formula is zi plus 1, and that is our f of zi. So now let's go to the rendering part. And what I will do is I will create 2 for loops. So for each I from 0 to width. So this is where we will do our calculations. But before actually writing the code for calculating the Mandelbrot set, we actually need to create a few functions. So the first function is actually a mapping function. So what we will need is to map the values from our width and height into -2 and 2. So we're going to map the values from xmin to xmax to a new set of numbers, to a new range of numbers. So in out min and out max. So let's actually implement the function. So I will call it map2. It will take for 5 parameters. So and we're going to return x minus xmin So this is our function. And then later on we will create another function for calculating color. But we will do it later. So the next thing we need to do is to import a few libraries. So we're going to work with complex numbers. So we will need the standard complex, very complex type, and then a few math functions for calculating the color later on. So color, standard C, math, and square root and log. Now let's actually move on to calculating the values. So the first thing I will do is I will create our z variable. So complex, and what we are going to do is we are going to map our I and j coordinates into a different range from -2 to 2. So I map 2 this is our first z. So what we're basically doing is we're calculating this. Now the next thing we need to do is we need to save our initial value of z in order to use it later. So auto zi equals z. So what we need to do next is to calculate the new value for z. And I'm going to create a new variable iter, and I'll use a for loop, and we're going to iterate the maximum number of iterations and calculate the new value upon each iteration. So in other words, we're going to calculate our z next from our z previous value. And then what we're going to do is to pass z next as an input to our function, and what we will get is a function of z previous. So this is basically what we are doing here. So auto z new or z next is our z times z. Now this is exactly what we did earlier here. So we have our f0th equals c, and this is our z first term, and then we're calculating the value of f of z1, which is c squared plus c. But we do not add that c term yet. We will add it later. Now if you're using a different language, you can actually do it manually, so it will look something like this. Now notice this is exactly the same thing as what we have done here. So we have our c squared, and then we found out that our c squared actually equals to a squared minus b squared, which is our real part. and then 2abi. So this is 2ab. But D automates this stuff, so it is already implemented. I can just do z times z. Now the next thing we need to do is to actually update our z value. So z times zn plus zi, which is our initial value here. So what we're doing here is actually our zn is z squared, right? And then we're just adding that last term, z initial. So here, zn is our c squared, and then we're adding our c from the previous calculation. And if you're using another language, that will look something like this. So now we have our new z value. What we need to do next is to check whether it diverges to infinity. In other words, does it shoot off into infinity? That is, if it escapes the xmin xmax boundary. We are going to use the if statement, so if z real plus z imaginary is greater than our max value, that is greater than 2. Now, according to Wikipedia, it should be zn in absolute value, but I won't use the absolute value since it removes some of the patterns from the Mandelbrot fractal. It's a lot more beautiful leaving it as it is, so we're going to break from the loop. And then what we're going to do next is to color the pixel into a certain color based on the value of our iteration. So that is going to be our color seed, and we're going to cast it into ubyte since our mapping function returns double. So we're going to iter, and we're going to map it from 0 iterations to 0 and 255. And then we will check if the iteration we broke off from the loop equals to the maximum number of iterations. And if so, what we are going to do is to set the seed color, the color seed, to 0. Otherwise, we will draw the pixel using that color. So that will be ij, and then color. That's it. Now what we should get is the Mandelbrot set. Xmin, xmax, oh, so right here, instead of xmin and xmax, it should be mmin and mmax. Now let's try to compile it. Oh, and it should be an assignment, not a condition. So save it and run it. Here it is. This is our Mandelbrot fractal. Congratulations. Now let's actually add a bit more coloring, so based on the color seed. So what I will do is, so as promised, we are going to create a new function that will calculate the color based off the color seed. So let's calculate the RGB values. Now this is completely random. You can do whatever it is. You can replace it with your own constructs. You can use different functions. You can use a sine, cosine, or whatever it is you want. So I will just use the square root of seed, and then I will map it from 0 square root 255, since it is the maximum range, to 0 to 255. So this is what I am doing here. And then, instead of specifying the color manually, what we are going to do is to use the color seed, and we are going to calculate the color like that. Let's do dub. Color expression line 97. Where? Oh, I forgot to use the mapping function here. So map to, and then like that. Should work now. Hey! It's a lot more beautiful now, right? And then let's change this white to black. That's it. Here you have it, the Mandelbrot Fractal. Now, for the final part, let's actually implement zooming in, zooming out, and keyboard movements so that we can explore the Mandelbrot Fractal more closely. So, what I will do in the very beginning is I am going to create a few sliders, a few variables. So the first two variables are needed to implement zooming in, zooming out, and then the iteration slider is needed to implement the depth, how deep we want to go with our calculations. And then the last two offset variables are needed to allow us to move around. So now let's actually implement this with our keyboard events. So the first thing is zooming out, and that is and I made a mistake here, so we should decrease the min slider. So how does the zooming out works? So what we need to do is to increase the distance between our minimum and our maximum values. So by increasing that distance, that interval, we're zooming out from the Mandelbrot Fractal, and subsequently doing the reverse will actually allow us to zoom into the fractal. So now we should be able to zoom in and zoom out. So let's test it. And right here, instead of mapping into mmin and mmax, what we are going to do is to map into mmin slider and max slider. And then right here as well. Now let's test it. So I'm zooming out, and now I can zoom in as well. And let's actually draw our FPS counter. Dub. So it's terrible, just 6 FPS. And the deeper we get, and the less is our frame rate per second. So the next thing to do is to implement the iterations sliders. That's it. Now, what we should do as well is we need to replace the maximum number of iterations with iter slider here as well, and then we should do the same here. And here. So let's save it and let's run it. Actually, instead of ES key pressed, let's make it ES key down. It will be a lot more responsive. So instead of pressing one key multiple times, we'll just press it once and wait for the result. So now if I decrease the number of iterations, well, the Mandelbrot set just disappears, falls apart. And if I increase the number of iterations, we get a lot more details in there. So now the last thing we need to do is to implement the moving around functionality. And then, before moving on, let's actually add another functionality so that we can reset everything to defaults. Now let's modify the code down here as well. So in order to be able to move around the screen, we need to draw the pixel So we need to add the offset X and offset Y. And then instead of else, I will do an if else, and so we do not want to draw the pixels that are beyond the window dimensions. That's it. Now it should work. So now I will compile the code to check if it works. It does work. And instead of compiling it in debug mode, I will compile it in release mode. Let's build it, and here we go. Let's decrease the number of iterations and then zoom in. Oh, that zooms out, and here we go. We can zoom in, and then so let's reset it back. So now we can move around the screen, and as you can see, the Mandelbrot Fractal is sort of cut off here. It's not rendered. And the reason we do not render it here as well is because it renders only because it depends on the window width and height. Our rendering surface is the same as our window dimensions. So what you need to do is to increase the rendering surface. So I'm not going to implement that in this video, but you can go to my GitHub account and download the code with this feature already implemented. And the reason I'm not going to do this is because it's pretty simple. Instead of using the window dimensions everywhere, what you should do is just add two new variables, the rendering width and the rendering height, and you should use them instead. And in the game loop, you should just what you should do is check whether the pixel is within the window dimensions, and if it's within the width and height, you just perform the usual calculations, and if it's not, you just skip it and continue to the next iteration. Alright, that's it for today. If you have any questions, write a comment below. I will see you next time, and have a nice day.